In the previous video, we introduced the mole and talked about some of its applications. Today, we're going to take a deeper look at chemical equations. At the end of the day, a chemical equation is simply a mathematical representation of a chemical reaction. A chemical reaction occurs whenever atoms are rearranged, and this rearrangement of atoms always results in the formation of a new substance. We can relate the idea of chemical reactions back to the notion of change. In chemistry, a substance can undergo two types of changes. The first type of change is called a physical change. Physical changes do not lead to the formation of a new chemical substance. For example, let's say I have a piece of paper. If I were to pick up a pair of scissors and cut that paper into 100 little slips, or just use my hands to tear it into shreds, no new substance is forming. The paper doesn't become something else. It's still paper, only smaller and less useful now that it's been ripped up. A chemical change, on the other hand, does result in the formation of an entirely new substance. One example of a chemical change is rust. If I were to leave an iron nail out in the rain, the iron will start to rust. The technical term for rust is iron oxide, and iron oxide is a new chemical substance. The nail wasn't originally made of iron oxide. The rain facilitated a chemical change that produced the iron oxide. A chemical reaction, then, is any process that brings about a chemical change by rearranging atoms and thereby forming a new substance. This right here is the chemical equation for one of the most important chemical reactions in nature. Photosynthesis is how plants make food, and this is the chemical reaction they use to accomplish this. On the left-hand side of this arrow, we have CO2, or carbon dioxide, being added to H2O, or water. On the right-hand side of the arrow, we have C6H12O6, which is the chemical formula for glucose. Glucose is a type of sugar. Along with glucose, we have O2, or oxygen gas. We probably know by now that plants take in carbon dioxide and output oxygen, which is the exact opposite of what humans and animals do. Now, in this chemical equation, there are a few things we need to notice. The substances on the left of the arrow are called the reactants. The atoms of the reactant molecules get rearranged during the reaction to produce the products, which are the substances to the right of the arrow. This means that photosynthesis uses carbon dioxide and water to produce glucose and oxygen in the presence of light energy, which is why the word light is written above the arrow. Light isn't a chemical substance in and of itself, but plants can't perform photosynthesis without it, so we include it for clarity's sake. We'll also notice the coefficients to the left of each chemical formula, and if we remember from last time, these coefficients tell us how many moles of each substance are involved in this reaction. So, all said, photosynthesis uses 6 moles of carbon dioxide and 6 moles of water to produce 1 mole of glucose and 6 moles of oxygen. The coefficients can also represent molecules, though, so we can also say that photosynthesis uses 6 molecules of carbon dioxide and 6 molecules of water to produce 1 molecule of glucose and 6 molecules of oxygen. Both statements are correct. We've already established that chemical reactions result in the rearranging of atoms. To actually rearrange atoms and make new substances, two things have to happen. Firstly, the bonds between atoms in the reactant molecules have to be broken. Breaking bonds between atoms requires us to add energy. In photosynthesis, this is where light energy comes in. Plants need the energy from light in order to break the bonds between the atoms which comprise carbon dioxide and water. Secondly, new bonds have to form to make the product molecules. Forming new bonds releases energy. This explains why a lot of chemical reactions can be somewhat dramatic or even explosive. Plenty of chemical reactions release heat, for example, and an increase in temperature is usually a sign that a chemical reaction has occurred. Chemists typically categorize chemical reactions into 4 classes based on how they produce new substances. The first class of reactions are synthesis reactions. To synthesize something means to bring 2 or more things together, and this is exactly what synthesis reactions do. They combine substances, let's call them A and B, into a substance AB which combines the atoms of both. The opposite of a synthesis reaction is a decomposition reaction. A decomposition reaction takes a substance AB and splits it up into substances A and B. The next 2 are a bit more complicated. Our third class is made up of single replacement reactions. We call them single replacement reactions because a single substance B detaches from substance C and combines with substance A, like so. Finally, we have double replacement reactions, where 2 substances switch places. This will all make a lot more sense once we start looking at some real chemical equations, so don't worry if this seems a bit nonsensical at the moment. Chemical equations include quite a few symbols, so it's a good idea to go over some of the most common ones. Every chemical equation will include an arrow, since this arrow separates the reactants from the products. We read the arrow to mean produces or yields. The plus signs separate individual reactants or individual products. We then run into these 4 symbols, these letters in parentheses. These symbols basically serve to tell us what state of matter the reactants and products are in. Not every chemical reaction will specify this information, but many will. Solid substances are denoted with a lowercase letter s in parentheses, liquids with a lowercase letter l, and gases with a lowercase letter g. If a substance is dissolved in water, it's referred to as an aqueous substance and has the lowercase letters aq in parentheses after it. All of these state of matter symbols are written to the right of the substance's chemical formula, by the way. The major requirement for any chemical equation is that it be balanced. A balanced chemical equation contains the same number of atoms on its left-hand side that it has on its right-hand side. The reason for this comes from the law of the conservation of mass, which tells us that atoms and other particles are neither created nor destroyed, even during a chemical reaction. Atoms are rearranged, yes, but they don't disappear into nothingness, or appear out of nothingness for that matter. Down here we have a chemical equation for the synthesis of nitrogen dioxide. We know this is a synthesis reaction because the reactants, nitrogen gas and oxygen gas, are being combined to form nitrogen dioxide gas. We know all 3 are in a gaseous state because of the lowercase letter g's in the parentheses. The major feature of this reaction, however, is that it is balanced. We can actually count up the atoms on both sides and see for ourselves if this is true. Let's start with nitrogen gas, or N2. Nitrogen gas is only on the left-hand side, and 1 molecule of nitrogen gas has 2 nitrogen atoms, as the subscript 2 tells us. There's no coefficient on N2, so we assume it to be 1. This means that there is 1 molecule of N2, which makes for 2 nitrogen atoms on the left-hand side. Oxygen gas is made up of 2 oxygen atoms, but there are 2 molecules of oxygen gas needed for this reaction. We go ahead and multiply the coefficient by the subscript to get 4 oxygen atoms. Let me say that one more time. There are 2 oxygen atoms in 1 molecule of oxygen, but there are 2 molecules of oxygen here. So we multiply 2 by 2 to get 4 oxygen atoms on the left-hand side. Now let's shift our attention to the right-hand side. There is a coefficient of 2 on nitrogen dioxide, which tells us there are 2 molecules of nitrogen dioxide being produced by this reaction. There is no subscript on N, so we assume it to be 1. 2 times 1 equals 2, so there are 2 nitrogen atoms on the right-hand side. For oxygen, the subscript is 2, so we multiply 2 by 2 again to get 4 oxygen atoms on the right-hand side. If we compare the numbers of atoms for each element on both sides, we see that they are all equal. This equation is therefore said to be a balanced chemical equation. All the atoms involved are accounted for, and that's the important part. Again, in order to balance a chemical equation, we need to focus on the coefficients and the subscripts. Multiplying them together is how we obtain the number of atoms involved, and knowing the number of atoms involved is how we account for all the atoms on both sides of the reaction. The coefficients, by the way, are also referred to as stoichiometric coefficients, and they tell us both the number of moles and the number of molecules of each substance in a chemical reaction. Remember, a mole is just a measure of the number of particles, and molecules are particles. We'll talk about how to actually go about balancing the equations in our example problems, since these methods are very mathematical and aren't exactly easy to explain using words alone. With that said, let's get into it. Example 1 says, check if the following chemical equation is balanced. This one should be doable, so please pause the video if you'd like to try this one for yourself. Before we do anything else, let's try and evaluate what exactly is going on here. On the left-hand side, we find our reactants. Our two players are Rb, or rubidium, and RbNO3. NO3 is the chemical formula for the nitrate polyatomic ion, so we know that RbNO3 is rubidium nitrate. This reaction is combining rubidium and rubidium nitrate to produce what exactly? On the right-hand side, we have Rb2O and N2. N2 is easy, that's just nitrogen gas or diatomic nitrogen. Rb2O, on the other hand, is rubidium oxide. This reaction uses rubidium and rubidium nitrate to produce rubidium oxide and nitrogen gas. Our next step is to count up the atoms on both sides. Let's write the three elements we're dealing with on both sides. We have rubidium, oxygen, and nitrogen. On the left-hand side, these 9 molecules of pure rubidium give us 1 rubidium atom each, so that's 9 Rb atoms. Then these 2 molecules of rubidium oxide give us another 2 Rb atoms, so we have a total of 11 Rb atoms on the left-hand side. Nitrogen has 2 times 1 atoms on the left side. That makes 2. Finally, we have oxygen, for which we multiply the coefficient by its subscript to get 2 times 2 equals 4 oxygen atoms. Right then, time for the right-hand side. For rubidium, we multiply the coefficient 4 by the subscript 2 to get 8 rubidium atoms. 4 times 1 gives us 4 oxygen atoms. And there's no coefficient on N2, which means there are 2 nitrogen atoms on the right-hand side. As we can clearly see, the number of atoms on the left-hand side does not match the number of atoms on the right-hand side. Because of this, we would conclude that this equation is not balanced in its current form. Example 2 would like us to balance this chemical equation. This example and the one to follow aren't necessarily for practicing on your own. They're primarily included to show the balancing methods in action. But anyone who feels as though they might have an idea as to how to balance this equation is free to give it a shot. The reactants are C6H6, or benzene, and O2, or oxygen gas. The products are CO2, carbon dioxide, and H2O, or water. As a quick aside, benzene is an important petrochemical, which means that it's found in petrol, or gasoline. This equation actually represents the combustion, or burning, of benzene. We might remember that any fire requires three things to burn. We need a fuel, we need oxygen, and we need heat energy. Benzene is the fuel, oxygen is over here as a reactant, and heat energy is added to break the bonds of benzene and produce the products on the right-hand side of the equation. All combustion reactions will include oxygen, or O2, as a reactant. Now that we know what's going on, we can add the coefficients. There are two ways we can do this. We can either use trial and error, or we can use algebra. Trial and error is simpler, but algebra is more efficient. Let's try algebra for this one. To use the algebraic method, we first add a variable for the coefficients of each substance. We'll use the lowercase letters a through d. Once we solve for these variables, we'll know the coefficients. To do this, we need to consider each element at a time. This reaction involves carbon, hydrogen, and oxygen. We can write equations for each of these three elements. For carbon, we look at each molecule involved and count up how many carbon atoms are in each. Let's start with benzene. Benzene has 6 carbon atoms, so we write 6A, or 6 times A. There are no carbon atoms in oxygen gas, so we write 0B, which is just 0, so that term cancels out. There is 1 carbon atom in carbon dioxide, and for that we write 1C. Again, no carbon in water, so 0D cancels out, and we're left with 6A equals C. We now repeat this procedure for oxygen and hydrogen like so. This is our system of equations for this reaction. We then use substitution or elimination to solve this system of equations. All this math, by the way, is basic algebra and is part of the prerequisite for studying general chemistry, so this shouldn't be a total mystery. If you are feeling a bit lost about the mathematical aspect of this, it might be a good idea to crack open an old math textbook and review how to solve for systems of equations, because this is probably one of the most important applications of this unit. Balancing chemical equations is also a very common test or exam question, so it's definitely worth knowing the math behind it. Anyhow, once we solve the system of equations, we will see that variable C is equal to 6A, variable D is equal to 3A, and variable B is equal to 15/2 times A. Our final step is to obtain the lowest possible value of A that will make all three of these variables equal a whole number. It doesn't matter what we choose for C and D because one whole number multiplied by another whole number always gives us a whole number. So we only need to worry about variable b, and the lowest number that will make 15 halves a whole number is 2. Variable a is therefore set equal to 2. B is now equal to 15. C becomes 2 times 6 equals 12, and D becomes 2 times 3 equals 6. This is our final answer. We need to combine 2 molecules of benzene with 15 molecules of oxygen gas to produce 12 molecules of carbon dioxide and 6 molecules of water. Alternatively, each of these coefficients could represent the amounts in moles. Last example now. Example 3 would like us to write a balanced chemical equation for the reaction combining nitrogen gas and hydrogen gas to produce ammonia, which is also referred to as hydrogen nitride. The problem also wants to know what type of chemical reaction this is. This problem is actually quite a bit simpler than the previous one, but there is a reason for this. Because this problem is simple, we can solve it using trial and error if we want to spare ourselves the math, or we can solve it algebraically. We'll use the simplicity to our advantage by solving this example using both methods. Before we can do that, though, we need to write out our equation. Our reactants are nitrogen gas and oxygen gas, which, if we remember, naturally exist in their diatomic forms as N2 and O2. And because we're exceptional chemistry students, we'll write the symbol for the gaseous state after each reactant. There's our arrow, and we're halfway done. Our only product is ammonia, and by looking at the name hydrogen nitride, we know that this substance has a chemical formula of NH3. Just by looking at this, we can note down the type of reaction being represented here. 2 reactants are being combined to form one product, which makes this a synthesis reaction. The synthesis of ammonia is very important in the chemical industry, by the way, mostly because ammonia is a major component of many popular fertilizers being used in agriculture at the moment. Ammonia is also used to make plastics and explosives, among other things. Now that we have our equation, we need to add the correct coefficients. Let's use algebra first. The 2 elements in this reaction are hydrogen and nitrogen. We'll use the variables x, y, and z for nitrogen gas, hydrogen gas, and ammonia, respectively. Oh, I'm sorry. This is hydrogen gas. For hydrogen, our equation is 2y equals 3z. And our equation for nitrogen is 2x equals z. If we put everything in terms of z, we obtain z equals 2x, and z equals 2/3 times y. If we assume z to be 1, we get x equals 1/2, and y equals 3/2. We have to convert these fractions to whole numbers, however. To do this, we multiply every value by 2. Variable z becomes 1 times 2 equals 2. X becomes 1. And y is now 3. If we substitute these whole number values back into the equation, we get N2 plus 3H2 equals 2NH3. To keep this video from going too long, I'm not going to verify the solution, but if we were to do so, we would see that there are now an equal number of atoms on both sides of the equation. If we don't want to go to all this trouble, we can also use trial and error for this problem. Before we add the coefficients, there are two nitrogen atoms and two hydrogen atoms on the left-hand side. And there is one nitrogen atom and 3 hydrogen atoms on the right-hand side. We can make the nitrogens equal by adding the coefficient 2 to ammonia. And we do this because it's the simplest step. We always want to begin with the simplest case and go from there. Doing so gives us 6 hydrogen atoms on the right-hand side. To make the hydrogens equal, all we have to do is add the coefficient 3 to the hydrogen on the left-hand side. And we end up with the same answer. Both these methods are valid, but generally speaking, I prefer the algebraic method. The math can be tedious, yes, but personally I find it less tedious than using trial and error. Unless the instructor specifies otherwise, it's usually okay to use whichever method is most intuitive to you, so there's a bit of freedom there. The point of this video was to introduce the concept of balanced chemical equations. In the next video, Unit 3, Video 3, we will reinforce this with plenty more example problems when we discuss stoichiometry in general. Thank you for watching.